So I'm just going to introduce our first talk. We've got Jeremy Stott, who's a software engineer, and he'll be talking about 3D printing in New Zealand. So hello, Jeremy.
Hello.
Welcome to your talk. I don't
Thank
know.
you. You can hear me all right? Everything's all
Everything sounds great. You look great.
great.
So I'm going to leave and let you get to it.
Thanks very much. Well, thank you everyone for tuning in to 3D Printing New Zealand. As usual, I've got a picture of a stable diffusion image, which is, I don't know if you've seen the images where you can give it a prompt and AI generates an image of roughly what you've inputted. It's a great procrastination tool for when you need to work on a talk. And so this one is a miniature model of New Zealand made with pancakes. And I think it nailed it. Although I'm a bit disappointed that the largest landmass looks like Australia and then New Zealand's off to the side. But anyway, we're on there at least. So yeah, 3D printing New Zealand. I want to start with a bit of background as to how I got to wanting to 3D print New Zealand. And it started with this project, which was to create a laser cut, I think it's bamboo actually, laser cut wooden model of New Zealand. It was a gift for a friend who was leaving work. And I had this idea that I could stack these laser cut out pieces of New Zealand and stack them together. And it was personalized with some data from from that friend who had collected some GPS logs around New Zealand. So you can see actually there's a little trace there, so that goes along. That's part of the data set that he had. And so yeah, it stacked all these models together, and it was quite a challenge to slice New Zealand up this way because this kind of data doesn't exist. And you can see a bit of the construction. There was each of these little panels was laser cut, and then there was a laser cut hole for a wire to go through. And I was really thinking about how do I make it easy to assemble. Still took us hours to put everything together, but hopefully letting the machine do most of the work. And you can see a little hint there as to what made it possible is on the underside of the model is actually the cutout piece for the next slice. So when the file that I sent to the printers was actually making really good use of the sheet. Actually, 100, like all of it was used because every piece is sort of the negative of the next piece is at the bottom of the previous piece. So I realized I only really had to do one pass with the laser, and so that was quite neat. I did get some funny questions from the the laser cutting company asking us what on earth it was, and so I sent them some pictures later on, and they were most amused also. So yeah, that project ended up quite well, and to do it, I found that there's this open source set of data for at least New Zealand, and I haven't checked in other countries, but New Zealand has a huge amount of topographical and geospatial data that you can play with, and it's mostly all open source license. I think it's sort of a Creative Commons attribution license. So yeah, it's really awesome. You can have a look, and I think I've got some of the, you can look through different types. There's an elevation model, which is where I started looking to go and pull out some of the slices of New Zealand, because a typical contour is sort of sliced horizontally, whereas I wanted it sliced vertically. So I got this data. And then what do you do with this data? And that's what I really want to talk about. One of the really neat tools was Google Colab, because it has a whole bunch of Python packages pre-installed, and you're pretty much ready to go. If you have a Google account, you can just spin one up. Alternatively, you could pretty much get up and going with the Jupyter Notepad kind of setup as well, which is what Google Colab is. It's like a Python notebook, Jupyter Notepad kind of thing, and it lets you write a little bit of Python and then see an output. And then that was quite handy because that let me sort of iteratively look at the data and plot it. And there's a huge number of Python geospatial tools available that make it actually quite interesting and easy to do. So you can see eventually I got a point where I could see, okay, this is one slice of New Zealand, including a little bit on the side. You see that square bit? That's the logo that we had from the company. So one of the really neat things was visualizing it at every step was really important, because it can be hard to know you're doing with this data and where it's at, if you're not always constantly visualizing it. So it was really handy to have this visualization tool that plotted out exactly what you're seeing at these intermediate steps, just so you can say, right, okay, this is what I want to look like, and you can very quickly spot obvious mistakes. When something's completely, the wrong way around or flipped or something, and you can rectify it straight away instead of, maybe hours later when you're wondering why it's flipped and where you have to go back to rectify that. And this is one of the final visualizations that I got to, where it was actually, okay, here's everything that I'm going to send to the laser cutters, so I could plot it and have it all laid out so it looked like New Zealand did. In fact, there were many iterations to get to this graph, many where they were completely wrong and had to sort it out, because it wasn't too expensive to get laser cut, but it was a couple of $100. So I wanted to make sure that I didn't waste a laser cut trip. So this was really great tool to be able to visualize it. But hang on, I hear you saying this was 3D printing New Zealand, not laser cutting out of bamboo New Zealand. And so here we've got these pancakes making up this 3D model of New Zealand. Also stable diffusion image. So that was a bit of background as to why I got interested in this project, because I wanted to make another gift for a friend. And this is major spoiler alerts for that one friend. So if you're watching, don't watch any further unless you want rocks for Christmas, I suppose. But anyway, this is the output image that I've got to, where this is a district in New Zealand, Kaikoura, on the east coast of the South Island, and it's this like, I can see a little bit of ocean, and it's got laser cut layers. It's got the 3D printed layers. So what is 3D printing? I'm not going to go through all the different 3D printers and all the different types and models and things, because there's actually a huge number of YouTube videos, that a massive rabbit hole. So if you're interested in that kind of thing, you can go and look at it. There's many videos that go review the different printers. So I'd recommend going and watching printer review videos if you're interested at all in the machinery. But it's essentially like these pancakes. It's just depositing layers. It's an additive process where it puts a little bit of plastic down, and then it comes along and does another layer on top. And so it's always going and adding a little bit more plastic, a little bit more plastic. And you can do some things like multiple colors. So you can have a layer of blue plastic, and it comes in these rolls, sort of these spools of plastic. I think this PLA is a plant derivative, which is quite nice, and it's fairly reasonably nice to work with. Some of the other plastics are not so nice to work with, but mileage kind of varies. Yeah, so going back to this, I had made this bamboo model, this laser cut one, and I knew that this geospatial data existed, and I thought I should be able to convert it to a similar thing, but for 3D printing. So I went back and downloaded that data again, and I came across a tool called QGIS, which is an open source tool, really lovely viewer to just explore the data in the first place. So this is literally, I downloaded it, and now I'm opening it in this open source tool, and I can have a look around it and see what it looks like. And it's this grayscale image. So this is what typically for height maps, 0 will be sea level, or and then your height will be the color value of the pixel. And there's some various technologies to stitch lots of images together, so you can get a really high resolution image without having to load the whole thing. So over here is actually Mount Taranaki. So yeah, this is what it looks like. It looks quite cool. But how do I begin to put this into a 3D model that I can print? Well, one of the problems is my printer's only so big. It's quite a small one. It's actually an entry-level printer, so it can only really print 20 centimeters by 20 centimeters. So, but I really wanted a big model of New Zealand, so I needed to cut it up somehow. And so back to the website I had, and there actually exists a data on the different districts of New Zealand. So here are the different districts, 67 of them. All of these have different district councils and all of their borders, and you can download this data as a shapefile. And so it'll let you then, I'll bring it up in here because it's a bit easier to see. So I have this shapefile data now, and so for all this height map, I can now have an overlaid portion of the district. I don't want to by hand manually go and cut this out, and this tool actually I discovered it quite late in my project. I actually think this tool could be capable of doing the whole thing by itself if I learnt the scripting language behind it. Um, but I decided to do it in Python in a similar way to the other one with the Jupyter Notebook this time. Um, so I've got this data, and so then I can explore what I can do with GeoPandas and some of the tools. So I should say one of the areas I went down, which was caused me months of effort, was you see that this district here, um, it has a border, but here it doesn't have a border along this coast. For some reason, all the other ones do, except for this one, and this is Auckland. And I think it's so that it can include out here, Little Barrier and Great Barrier Island. But that made it really difficult to accurately cut the shape, and so I had all these workarounds to try and cut it. But actually, the real solution was a friend said, "Well, surely there's some better data out there," and there absolutely was. There was same website. It was just slightly different in a different category where they'd gone to the trouble of clipping the data for me. So, one of the lessons I've learned a lot is, the better the data going in, the better experience you're going to have. If you can find the best source going in, then you're going to have a much better time down the road, and you won't be fixing things that aren't real problems. They're just as a result of not having the right input to start with. So this has helped. A huge amount by having a better shapefile of the different districts. And so the idea is I cut them out per district, and then I can assemble them and have a puzzle, essentially a puzzle of New Zealand, and they'll be scaled based on the largest district, which I think is Southland, right down here. So however this big one can fit on my 3D printer, that's how big it'll be. So let's see what I've got next. I mentioned that. Right, so some Jupyter Notebook stuff I have prepared. Jupyter Notebook. Now, don't worry about any of the code in this because it's really janky Python. It's pretty much the real code that I had, and but the code's not the important part. It's going to be more the process in how I went through taking the data and ending up with the model I could 3D print. And if you're interested in this, I'm going to try and make this available so you'll be able to access it, download it, and mess around with it if you like. So I can essentially just load that file with this package called raster.io, and then that's the one that's essentially going to do most of the heavy lifting from the rasterized height map point of view. So I load that in, and I can print some interesting stuff around the map projection, because you're going to have to unwrap the spherical projection of New Zealand onto a flat surface. So that's not always done in the same way depending on where you are in the Earth. So they have different map projections, and so, but you can essentially just try and get that visualized straight away. So here I can just basically plot the result, and you can see all these different tile sets. I have this area where it's just completely dark, and that's where there's no data. So I decided to clip that off, and so now I have something similar to what I had in that other package, and I can send pretty screenshots on Signal to people going, it's working. Then the district shapefile, I'm using GeoPandas, and it's essentially just like read the whole zip file, which you download the zip file and it's pretty much in the correct format because the people that put the lens data together are lovely. It's in the correct format to be read straight into GeoPandas, and so this is what the data looks like. And we've got some things that look like district names, and then over here something called geometry, which looks like the geometry of the shapes. And so we can plot that as well. And so here's all of our districts, which looks lovely. Then I can extract a single district. I can say, well, what does Auckland look like? And here's that model of Auckland. Now, the main piece to combine, how do I now cut out the, height map of the New Zealand with the shape of Auckland? I found a really lovely function in the raster.io package called Mask. I love connecting libraries together and letting them do all the heavy work for me. I went down a little bit of a rabbit hole trying to do this myself, and I'm like, nope, this is a bad idea. Actually, there's these two packages that kind of work well together, even though one of the inputs is a vector data, essentially the points of the shape of the outline, and the other one is a raster image, which is a height map. Turns out you can kind of almost mask them together, and you can get now the clipped just height map of Auckland, which I can't download somewhere, right? Why don't I just go and find a 3D model of New Zealand online? Well, I won't be able to find a 3D model per district, right? So I won't be able to create my puzzle piece. This is why I've gone eventually down this road. So then to convert this height map now into some kind of mesh that I can use, essentially what I'm going to do now is create a grid of triangles. And then for every vertex in the triangle, I'm going to just set the height to the coordinate from the mesh grid. So this took a bit of messing around, but eventually I can get this mesh here that renders very slowly because there's something like a million triangles here, just taken from exactly from that height map. So I tried to process this data, but it's just way too slow because it's far too much detail. I think this is like a 50-meter interval height. So at every 50 meters is like a measurement for the height. That's just a bit too much for my poor 3D printer. You're not going to see any of this data anyway. So I ended up simplifying it. And there was another Python package to simplify a mesh. This was using some quadratic mesh simplification formula where it will try and keep the details and then simplify away areas where there's not much change going on. So I just found this package and it seemed to do the trick very nicely. So now you can see the same model and it's simplified. And I've also taken away the kind of ocean floor area where it's just basically just exclude everything that's zero. And so now we have this model. It looks like Auckland if you look from up here, but this is obviously the hills are not that steep, so we've got to do some figure out what the scales looking like, and that's just to go through. Essentially, this is the steps from the beginning. Just load it from our data, flip it around the right way, and scale it, and then go through all of the grid, and then assign our value from the height map, and then throw it through the simplify function, and then I can just plot it with this tool. So now we have a much better looking mesh of Auckland. This could be useful for a game, actually. I was thinking about this. I don't know if you've seen this Sebastian League on YouTube has made a really lovely series of videos covering her flying around on Earth with a little plane, and that came to mind when I was thinking, oh, this is quite neat, getting this kind of data and what you could do with this. So then the next process was to turn this into something I could print, and there's a bit of a problem. There's a hole in the bottom, it's just the outside shell, and the other thing is if I printed this, some of these parts would be impossibly thin. So I wanted to add a little bit of a base to it to give it something to print onto, so it's not just printing a tiny little speck. That's not going to be a very fun puzzle to put together because, you're going to lose these little islands. So I really wanted a bit of a base, and to do that, I needed to close the model. And I thought for a long time how to do this, because it's sort of one of those things that sounds simple and then is very non-trivial because I have all these different islands. So I can't really say for any line that I have, for any triangle in this model, well, how would I close it? It's almost mind-bogglingly difficult if you try and do it manually. What I ended up doing was just taking that same, looping through that same list for all the faces, and instead of setting the height to be the height from the height map, I just set to 0. So it's just like I squashed the whole thing down to 0. So I ended up with the same model but flat, right? And importantly, though, it's the same outer shape, and then I can just slap those two together. So now I have a bottom face on the model. It's probably not going to be a perfect model from the 3D model package point of view. It's probably going to complain that there's a whole bunch of errors, but that's okay. It's going to deal with it, and that's great. So that I don't have to deal with it. And this is the point where I dove into this library called CAD Query, which is to also in Python to now start manipulating these shapes. So I can pass in this bottom shell here, this bottom face, and I can extrude it. So that's essentially what I've done here. I've managed to get all those lines into the format that CAD query is expecting, and then make a shell out of it, and then you use this weird notation where you create an object and you create some wires and you can extrude from that. This took a lot of searching to figure out how to do this. It looks like I'm doing something a little bit unusual for the package, so that can be a bit tricky when you're doing something that's not really designed for. CAD query is really a parameterized modeling package that you wouldn't load in an external shape like this in, but to be able to extrude it in this package was extremely helpful because, again, it's something that's going to be very difficult to do, yourself. And the other thing I want to do is, after I put these together, I'm going to have them as magnets. And I don't know if you can see behind me, I've got actually some of these stuck on my thing, on my kid's magnet board that I've stolen. These I want them to stick up on the fridge or something as the final piece, right? Or eventually maybe on a displate style, printed ocean steel plate thing, so I could plop all these models together. So I really wanted to put a magnet inside each piece. So with this CAD query package, you can model a magnet, like a housing for the magnet, and that's just, you can do some sort of, this is really how it's meant to be used, is to say, okay, I've got a plane and I'm going to create a circle and then I'm going to extrude that, by some dimension. And so now I've got a little disc, but then I can then extrude it further, create another circle and have a little hollow piece. So now I've got a kind of a little cup that the magnet could sit in, and then I'm going to put a lid on top. So this has the hole in the middle, right, for the magnet, and it's kind of ready to go. This then I'm going to union into that solid that I extruded. So, and you can do that. You can grab all of those, grab the faces. So yeah, it's another feature of this is to say, okay, I want to grab all of the faces with the lowest Z value. And so it's going to go through and say, okay, well, actually those faces are on the bottom. So it's highlighted them here. Again, this visualizing it every step is just so useful for this stuff. So I can see the faces along the bottom, and I want to be able to find out where to put the magnets. So I can basically iterate through all their faces now and figure out what the area is. And because I want magnets under some of these islands, for example, and so I can grab the area, and then based on the area decide, do I want a big magnet or a small magnet to plop in this spot. And then here's the similar kind of thing that I was doing before with the circles to make the geometry for the magnet hole, and then here it is inside the model. And so you can see it's chosen to put one there, which was, I think, the center of mass for this large piece, and then one over there on that island, and then some of these it decided it was too small. Well, I decided because some of them were just, otherwise I don't have that many magnets, and then that's how I decided to put them everywhere. And then basically you can add the top back on, which is, I don't know if you can see it so easily, but now we've just basically added in that top mesh, and we essentially have the geometry ready. We've got now our top mesh that's made up of all these triangles. It's simplified so that we're trying to save on processing time, and so we've got some detail where we want detail, but we've got some simple pieces. I don't know where the simplified pieces, but it's there somewhere. You can see the kind of dense areas are where it's kept a bit of the detail, and some of the light areas where it's decided, that's a bit of a flat area. And finally, I also included a buffer on the geometry because I didn't want to lose all the detail of these islands. And really, actually, Marlborough Sounds caused me a lot of issues because Marlborough Sounds was so detailed that it just too flimsy. When I tried to print it, it all just fell apart. So around here, you can imagine like all these little spots and things. It tried to print them, it tried to go around and do it, but it's only so accurate, so it didn't really do a good job. And you can see this whole landmass is held together by this little piece here. So, at a small scale, it just doesn't really work so well. So to fix that, I added a buffer around all of Auckland, and well, actually every piece. What you see here is happens. This is a project that happens to every single district, and so you can see here now the height map with the buffer applied, and then I've used a trick to cut out from each piece the the buffer of the model of every other piece, because otherwise they're not going to fit together anymore, if that makes sense. So I've added this buffer, and now I've actually got areas at the bottom of Auckland that are not part of Auckland, they're part of Waikato. So I needed to cut those back out again, and so I just basically did a cut operation. So again, it's lovely to use these libraries because there really was just a cut, so I can do here. You can see district with buffer dot difference, and so that was the actual geometric operation is hidden in the library, and I get to just kind of connect them together, which even made this project possible in the first place. So yeah, then we end up with this final model, and we can export it and then load it into our program for our printer, which in this case is just a program called Cura. It's a slicer. And so now that we're handing it over to our printer software to say, here's the model I want to print, and can you figure out what to do with it? And so when you hit slice, then it goes through your model and figures out where it should actually put plastic. And it's a very complicated algorithm that, that different manufacturers put together this pro package. Cura, I think, was based on an open source one originally. I'm not sure. There's another one, Prusa Slicer, and a whole bunch. So if again, I don't want to go into the details of which, all the different printers and things, but if you go down that rabbit hole, you'll need a slicer to then create the machine code to send to your printer, which actually moves the printer around and squirts out the plastic. So it'll slice that up and come out with where it's going to pop it. While that's calculating away, I'll just go through the last little bit of some action shots of what it looked like. Here's that first attempt, and you can see Marlborough Sounds was just too flimsy. We'll just skip over that bit's not going to be that great. Oh, it might work. This was just to show you that I've got a printer to stop at a particular layer, and then it's going to ask me to put the magnets in, and then I can put the magnet on each layer, and then it'll continue printing over the top of the magnet. So that's where it's the cavity, right? The magnet's now like kept inside the model, and it won't come out. This was really nice in practice, in theory. In practice, it means that I need to be there at every step to put it in. So maybe I should just had a hole and glued it. I'm not sure yet. To give you an idea of the scale, I just had a map and they magically lined up. It was very lucky, just by chance. So it's 1 to 1.7 million scale, I think, just because of what that map is, roughly. And here you can see the improved version where I've started to add the buffered area. And so the magnets, that's put the plastic on top of the magnets, and then this is the result that I've got now. So yeah, really liking this. It's looking great. I need to do a little bit of tweaking for the puzzle pieces to fit together a bit better. They don't mesh as well as I'd like, but I can tweak that, and then I'll be able to print out the rest of them and have them going. So I think I have. Yeah, they look spectacular in person. So I'm sorry, you're gonna have to imagine that they look really lovely, but you can see the detail is just so great, because you're almost expecting contours anyway from seeing contoured maps, and so when the printer leaves the layer lines, they actually become part of the model, rather than an artifact. Yeah, so I think that's about all I've got. A final pancake picture, and if I've got time for a couple of questions, otherwise I'll be around to answer them in the chat.
Hello. I think there was just one question from Jerome, who just wanted to know if you had any experience with Python before you used this project, or do you have a bit of a learning curve there?
I have had experience with Python before this, yes. Even though you wouldn't know it from my code. So yeah, I have used Python a bunch, but the Jupyter notebooks and the Google Colab make it really accessible. So you really can mess around and start playing with it. And so I haven't really had much geospatial, programming experience. A little bit of Python experience helps, but honestly, you don't need much. It's just calling some functions and maybe iterating over some things. So it's really a great project to start learning a language like Python. You don't have to get into any of the more complicated parts of the computer sciencey aspects, I suppose. You can just stick to the pure functional, as you'd be thinking about the process, write it down in Python and see the result. So it's quite satisfying from that point of view.
Awesome. Thank you. That was an awesome talk. I can do 3D modeling, but I cannot do all of that coding. So a lot of it went over my head, but I was still very interested.
Well, I can't do any 3D modeling. This is my only way. So I hope maybe I'll get to the middle at some point, and then I can
have a discussion. Yeah, cool, awesome. Thank you so much.